Right, hi guys, welcome back. This is video 1 of Unit 7, which is Computer Vision Fundamentals. And I just want to introduce you to a few terms, so convolutional neural networks, data augmentation, and transfer learning. So they do pop up a few times in the exam, and I just think they're quite an easy way to get some marks and improve the understanding from the course as well. Hopefully this will be the supplementary bit of learning that can really help you wrap your head around what's going on. So let's dive into it. I've got some really simple slides for this one. I think it's best to keep it simple and just talk a little bit. So convolutional neural networks, or CNN, sometimes known as, they're really quite simple actually, and they're a form of neural network that will take in an image as the input. So we're thinking back to our 3 general layers that all neural networks have: the input, hidden, and output. This input just takes in an image, right? That's the only difference. Or it could be a video, right? You could take in a video, because a video is just many frames and many images per second, per minute. So it really is just the same kind of thing behind the scenes. So here we're looking at a handwritten digit, so 2, handwritten 2, as our image, and it's being fed through a convolutional layer, and it's being output to some amount of layers here, right? So let's we'll build up as we go into it. But the main takeaway from what we're looking at here is the convolutional layer really is built off this little square here. So what's going on is we have this little square will plod along this image one step at a time. We'll have another one here, and then after a little second we'll have another one here, or have another one down here, and it keeps moving along, right? Kind of continues, and we'll get it to cross our whole image in order to break down our image into smaller pieces so we can identify what's going on in that smaller section. And so why are we doing this, and why are we interested in doing this, is the first kind of question that should spring out to your mind. And the reason for it is rather simple, really. We're just trying to break things down really visually to see if there are smaller features that can give us clues to what's happening in the broader scheme of things. So if we were trying to identify cats on images, you might not need to see the whole image to be able to identify it as a cat. You might just have to see the fur on its back and its cat-like ears, or the whiskers, or the tail, or the little cat paws, right? And you could determine just from that smaller section, oh, this must be a cat. There's very high probability, right? And that's kind of what we're going on here. We're trying to say to the model, we're saying, okay, let's not take the whole model itself, the whole image itself to start with. Let's just only focus on, say, the top half, right? Or we might go even smaller. We might go the top quadrant here, or even smaller. Maybe we'd be interested in here, or whatever it might be. We're going, what's going on in that smaller section? Is there any clues? And as abstract as this is, we can actually see that straight away. So if we were to look at only the top half of this image, and we'd have this big curly 2 going on here, but we don't know it's a 2 yet. So this big curly thing, it doesn't tell us what it is, but it definitely leads us to believe that it's certainly not something, you know. We might be inclined to think, oh, you know, it could be a 2. It also could be a 3, right? It could be many things, but it really is not a 5, right? It's very unlikely that this would be associated with a 5. So just this alone here, in looking at the top half, is enough to tell us some really key features, right? Some really one of our nodes in our network could be lighting up and going, okay, this is already looking a lot like a 2, or maybe another 3. But so looking at the other subsection, we would be able to determine, okay, yeah, maybe that's a bit of a bottom half of a 2 going on. Could be many things, but that's why we're breaking it down. Okay. The only other thing to mention about a convolutional layer is that we are effectively duplicating our data quite a lot here. So it's a downside. For every square here that's going on, we are effectively, if our square is covering many parts of the image over and over and over again, we're effectively multiplying out our data size. So our image is being represented many times. And if we're doing it, like I said, in different sizes, so maybe one's half an image, one's a quarter of an image, and then there's many smaller bits of images, then we're effectively multiplying many, many times. So that is what is the meaning behind all these layers over here, or these representations of the picture. Okay. So what often goes hand in hand with a convolutional layer, because of this, is a pooling layer. Now, a pooling layer compresses our data. So it's helping us to reduce how many of these images are being kept and stored to be trained on, which is really important. So as we're dealing, so let's say with videos, we might have many images to go through per sample. And in that case, we'd be really computationally expensive, and we want to minimize as much as possible. So pooling would be very important. Okay, so quick note on pooling. So pooling, this is would be our compressed image here, 3x3 matrix, you could think of it as, thinking back to your matrix video, compared to the original image here. That's a 5x5, right? 5x5 table. And for every part of our 3x3 pooling layer, we would be representing a larger portion of the image. And essentially what we'd be doing is we'd be selecting some bit of our larger portion of image. Let's say that we're interested in this. We're going to be taking either the average or the max or the min, depending on what type of pooling is going on, and storing it in that value there. So here, this is an example of max pooling. And you can see we've got 3 is the biggest number in the big square. So that's why it's represented in the top left-hand corner there. Okay, so, and this will go on for all of the iterations. So for the middle top, we'd be looking at this middle top here, and that's still a 3. That's why 3 is represented in that square. And similarly for the shaded region, we can see that 2 is the max in this square. So therefore, that's why 2 is represented in here. Okay, so we're effectively disregarding a lot of data in favor of keeping the most important in a very cheap, very cost-efficient way of doing it. Okay. Now, data augmentation. I'd like to just introduce you to this because when you're dealing with images, it's not often that you have a lot of sample data to build your network from. It's quite common that it's very hard to get a hold of this data, especially if you might be, let's imagine we're dealing with a network that might be trying to classify different types of medical imagery, such as cancers, or you're interested in doing some sort of security protection. It's quite hard to get that CCTV camera footage, right? So having a way to generate more data without actually having any unique data that you've gone and collected is really good. It's really nice. So increasing that sample size, that's always a good thing. So one way that we'd be doing it is data augmentation, right? It's a very cheap, very cost and time effective way to do it. So with data augmentation, we're just taking our bit of data and augmenting it, so changing it in some small way to therefore have more sample data that is very similar, but different in some way to improve our generalization of our model. Okay, so let's look at some examples. On the right here is some classics. We have decolorizing or edge enhancing, and especially flipping and rotating. They're all classic examples of data augmentation. So on the left, if we had our true label, which we should have in most machine learning problems, let's call it B for butterfly, right? All of these other ones on the right would also be labeled with the true value, right, when they're fed into our model. And so therefore, our model would be able to generalize all these other new features, like the butterfly being able to rotate or having a different color scheme associated to it, to that attributed output that we might be trying to classify, let's say. Okay, so data augmentation is really handy for increasing our training set or test set or the whole data set when we're looking for a fast and cheap, cost-effective way to do that. Very, very quick and handy. And finally, so transfer learning and fine-tuning. I just want to introduce you to this. So transfer learning and fine-tuning are very popular ways of being able to create new models. And one of the tricky things with creating new models is that it might be very, very very costly, and time cost associated to it, in order to create a suitably trained, accurate model, right? So very high cost, very high time to produce. And so transfer learning hopes to help that. Okay, so what transfer learning is we could have a teacher model, which we could call BERT for now. It's one of Google's large language models. And we would be using BERT, one of our teacher models, to train, fine-tune our student model. So what's going on here is that we're depending on an already built, very large, very, very expensive model. And we're just going, okay, we'll take, let's say, 90% of the effectiveness of that. And we'll then have this sub model, which we can then train. So that's fine tuning. Fine tuning is training towards your specified need, to make it very appropriate, very accurate on a smaller subset. So perhaps BERT could be fine tuned into a call center as a service neural network for a business need. And that would be representing your network here as a student, right? And this is a very, very popular framework that's being used currently. So it's a good way to get around very complex network solutions that are needed, and doing it in a very cost-effective and cheap way. So such as image or video models that we've seen here, getting around all of this architecture problems, which are really half of the problem, by leaning on those big brother companies, your Google, your Apple, your Nvidia, leaning on their models and then using their models, transfer learn, and fine tune their models onto your model, right? All good. I'll leave it there. I'll see you in the next one. Thanks, guys.